Hello, we're going to be going through the midterm 2 questions for the fall 2017 final for MA266. Question 10, a spring mass system is set in motion and its motion is determined by this initial value problem, u double prime plus 100u equals 0. So we can take our characteristic equation, r squared plus 100 is equal to 0, or r is equal to plus or minus 10I. Therefore, u of t is equal to c1 cosine 10t plus c2 sine 10t. That's looking pretty good. We can solve for our cosines and sines by taking u of 0 being equal to 1. That will just cancel out this term here completely and leave us with a 1 c1 over here. So c1 is equal to 1. And then solving for u prime of t is equal to negative 10 sine 10t, but we didn't even have to write any of that because u prime of 0, this sine term will just go to 0. The only portion that matters is plus 10 c2 cosine 10t. And we see that this is equal to negative 10, so c2 is negative 1. And we know that the amplitude of the motion is just this coefficient a, which happens to be 1, so a equals 1, and b right here is negative 1. The amplitude is c. That's the square root of a squared plus b squared, so 1 squared plus negative 1 squared is 1 squared, so we have root 2. 10 is E. Question 11, we have a homogeneous differential equation given here with two solutions, y1 of t, which is t squared, and y2 of t, which is t cubed. We're using variation of parameters to solve for our general solution. The first thing that you should check always to make sure that we don't forget it is that we have a t squared multiplied by y double prime here. In order to use variation of parameters and to get the correct f of t term, we have to have a coefficient of 1 on our y double prime. So we can rewrite this as y double prime minus 4 over t y prime plus 6 over t squared y is equal to t. So collecting the four terms that we need for our variation of parameters, we have f of t, which is just that right side of our equation that we found, the only bit without a y when the coefficient on y double prime is equal to 1, that's just t. We know that y1 of t is t squared, and that y2 of t is t cubed. And we're also going to need the Wronskian of these two solutions, which is the determinant of t squared, 2t, t cubed, 3t squared. That will be 3t to the fourth minus 2t to the fourth, or just t to the fourth. T to the fourth, like that. Okay, and we're setting up yp of t as being equal to negative y1 times the integral of y2 times f of t divided by the Wronskian dt plus y2 times the integral of y1 times f of t over the Wronskian dt. We can go in and replace all of our y1s with t squareds, all of our Wronskians with t to the fourths, t to the fourth, all of our y2s with t cubed. No, that's not a y2. T cubes, and all of our f's with t's. There we go. So in this integral, we get 1 over t, and over here we just get 1 dt. Computing these integrals, we will get minus t cubed, dropping our term with the c on it that would result from this integral, and then plus t cubed ln t. And some alarm bells should be going off in your head as they kind of are in mind that we don't have any plus t cubed terms in our particular solution section of y of t, but we'll see that that gets solved pretty quickly. So this is our, not yc, yp of t. Yc of t will just be c1 times y1 of t, which is t squared, plus c2 times t cubed. And you'll see what we can do when we compute y of t as just yp of t plus yc of t. This minus t cubed can just get absorbed into this constant term when this t cubed is added to that t cubed. So we end up with c1 t squared plus c2 t cubed plus t cubed ln t, which is option A. And 11 is A. Let's find the general solution of this fourth order homogeneous differential equation. We can pull out our characteristic equation, r to the fourth minus 10r squared plus 9 is equal to 0. And how will this factor? Well, actually, let's do a substitution. Let's say that u is equal to r squared. So this becomes u squared minus 10u plus 9 is equal to 0. This is just for ease of factoring. We will get r minus 9, r minus 1 is equal to 0. Well, actually, this is u and u minus 1, and then we can undo our substitution and replace these with r squareds. And really, that's just a semantic difference. But solving these two, we will get r is equal to plus or minus 3, r is equal to plus or minus 1. So our y of t should give us c1 e to the 3t plus c2 e to the negative 3t plus c3 e to the t plus c4 e to the negative t. And if we look around, I see that in option E. And 12 is E. 13, which of the following is the correct form of a particular solution to this equation right here? So they're asking us to find what our guess would be for, for using undetermined coefficients, but it's so complicated that they don't want us to go and compute the rest, which is nice of them. So let's grab our characteristic equation. This is r to the fourth minus 1 equals 0, so r to the fourth equals 1. This has roots. R equals plus or minus 1, r equals plus or minus I. And what this means is that our yc of t will be composed of c1 e to the t plus c2 e to the negative t plus c3 cosine t plus c4 sine t. So anything that has the same form, some constant times cosine, some constant times sine, or some constant times e to the t or e to the negative t, that we see up here, we will have to multiply by enough t's to get out of the way of an overlapping term with our yc. We see that 3t e to the negative t is good. That doesn't overlap with anything, nor does this 2, but this 2 sine t is no good. And so our ypg, our guess for y particular, will be, well, we said that 2 is good, so we can say some constant a plus some constant bt e to the negative t. We also said that was good. And remember, whenever we're doing this kind of guessing, whenever we see a sine, it has to be sine and cosine as a conjugate pair. Not a conjugate pair, just a pair. So we'll have plus ct sine t plus dt cosine t. And remember, we are multiplying these by t so that we don't have some constant times sine in here and some constant times sine in our guess for y particular. And that leads us to, oh, I do see the mistake I just made. And instead of cutting, I'll go and show you what it is. If we are guessing something when we have something in this form, so some constant t e to the negative t, this will get expanded to, let's say this is just the exact case that we have here. Our guess for this term would be a plus bt e to the negative t. We have to expand that polynomial out like that. And as a result, that actually shows us why our current guess is flawed, because if this was our guess for this term right here, we would have some constant times e to the negative t, which we know is already present in our yc. So all of this has to be multiplied by t. So I'm going to go and completely rewrite this this solution. We will have yp of t as being a plus t times b plus ct e to the negative t plus dt sine t plus et cosine t, and that really should be a capital E there. Let's take a look. I see D is looking identical, and it's correct. Let's find the Laplace transform of this function here. If I can grab our little Laplace transform sheet, that'll be helpful. Let's see what is happening here. We have a piecewise function. We can graph this out. From 0 to 2, our function is equal to t, and afterwards, our function is still equal to 2. So we kind of have this infinitely fast change in the slope of our function, but we're so continuous everywhere. But what we can do is model this with unit step functions. So the unit step function at 1, I'm not sure if saying at 1 is completely correct there, but u1 of t is a function that for all t before 1 is equal to 0, and then at t is equal to 1, it jumps up to 1 and continues there for all t. And this value c here, it's called c in our tables, this value c controls what value t this function quote unquote turns on. So we can use this fact to model this. From between 0 and 2, we want our function to be equal to t, so we can have t times 1 minus u2 of t. Let's see what this will do. Well, when t is less than 2, this will just evaluate to t because u2 of t will be 0, but when t is greater than 2, u2 of t will be 1, so this whole bit will evaluate to 0, and our function will be done there. And then let's add 2 times u2 of t. Okay, this is looking good. Let's rearrange things though, because right now it's not really in a form that we can take our Laplace transform very easily. And so we have t minus t u2 of t plus 2 u2 of t. So we can rearrange this in the form t minus u2 of t multiplied by t minus 2, because that will expand to our 2 u2 of t and our negative u2 of t multiplied by t. Okay, so that's good. This is our f of t. Now if we want the Laplace transform of f of t, things are actually looking pretty good, because right down here we see that the Laplace transform of uc of t times some function of t where all the t's have been replaced with t minus c's is just e to the negative cs multiplied by the Laplace transform of the original function of t before we replaced all of the t's with t minus c. So dealing with this portion first, this is going to be minus u2 of t, so t is equal to 2, e to the negative 2. I'm using alpha as my variable. Deal with it. And then our function f of t is just t here before we replaced it with t minus c, which is t minus 2. So our Laplace transform of t is just 1 over alpha squared. So we have over alpha squared. And then finally, the Laplace transform of t by itself is just 1 over alpha squared, so we can add 1 in there. And that gives us answer choice A. (15) If y of t is the solution to this initial value problem, then what is y of t? We know that the Laplace transform of y double prime is equal to alpha squared y of alpha minus alpha y of 0 minus y prime of 0, and that the Laplace transform of y prime is alpha y prime minus y0, and I won't write it, but the Laplace transform of y is just y subscript alpha, the way that I am writing things out. So let's take the Laplace transform of both sides of our equation here, both sides of our equation. So y double prime will become alpha squared y alpha, and both of these initial condition terms, and in fact the one down here too, will all be equal to 0. It's always really nice when it works like that. Plus 4 alpha y alpha, transforming this 4y prime, and then plus 5 y alpha is equal to the Laplace transform of gamma of t minus 5. Yet again, disclaimer, I keep forgetting to look up whether or not this is actually called gamma. Okay, the Laplace transform of gamma of t minus c is e to the negative cs. So our value of c here is 5, so we will get e to the negative 5 alpha. Rearranging things a little bit, we can factor out a y alpha on this side and have alpha squared plus 4 alpha plus 5 is equal to e to the negative 5 alpha, and we can divide that over. Alpha squared plus 4 alpha plus 5. And this is equal to our y alpha. And let's see what we can do now. There should be, given that all of our answers are only one term, there should be some relatively easy trick that we can play to work this one out. We see that a lot of them involve uc of t and sine of t minus c. So let's take a look and see if we can find that in here. uc of t and t minus c. Yeah, here we go. So we have a function in the form e to the negative cs times some function of s, or alpha in our case, and the inverse Laplace transform of that is u c of t times the inverse Laplace transform of this guy right here, but we'll replace all of the t's that we get with t's minus c. So let's see if we can pull that off. I'm going to take this guy down here and mess with it a little bit. Let's say that this is 1/2 times 2 divided by alpha plus 2 squared plus 1. Oh, and in fact, because it's plus 1, we can get rid of that. Okay, so now we have things in a form where we can use where we can use this transform, this guy right here. So we have some value b, which is 1 in this case, and some value a, which is -2, and so we can perform this transformation. So overall, we are getting y of t as being, remember that this e to the -5 alpha will become u5 of t, and then we're transforming this guy normally, but replacing all of the t's that we get with t minus c. So e to the at, where our a value is -2, t minus 5, and then the sine of t. But instead of t, we have t minus 5. And looking at our answer choices, this seems to match up with B. And the answer key agrees. Very nice. Okay, 16, we're finding the inverse Laplace transform of this. You might be tempted to try to figure out something right off the bat, but you know deep down that we're going to have to do a very uncomfortable partial fraction here. So that's what we're going to do. Alpha plus 7 divided by alpha minus 1 times alpha squared plus 2 alpha plus 5 is equal to some a over alpha minus 1 plus some b alpha plus c over alpha squared plus 2 alpha plus 5. Excuse me. And the reason that we're okay, just to pause for a second, the reason that we're okay with having a term so big like this, because usually, remember, we want to split things up so that we just have alpha minus some constant. That's a form that we really like to see. But here, this is kind of a special case because we can change this term up to alpha plus 1 squared plus 4, which will be very nice if the term that ends up on top of it is something that we can use for either of these inverse Laplace transforms. And given that, well, I don't want to give too much away, but given that we're seeing sines and cosines here, I think it's relatively likely. Okay, let's get going with this. We're going to multiply our denominator up into everything, and so we will end up with a alpha squared plus 2a alpha plus 5a plus b alpha squared minus b alpha plus c alpha minus c is equal to alpha plus 7. So a alpha squared plus b alpha squared is equal to 0, so a is equal to -b. A is equal to -b. We can equate the constant terms also. That's 5a minus c is equal to 7. And what else? What else do we have here? We see that 2a alpha minus b alpha plus c alpha is equal to 1 alpha. 1 alpha. So we can divide all those alphas out. And we are going to put this into a matrix to solve it a little bit more easily. We can rewrite this first line as 1, 1, 0, 0, where this is our A, B, C, and our equals whatever position. We have 5, 0, -1, 7, 5, 0, -1, 7, and 2, -1, 1, 1. This is the same as, let me duplicate everything over here. This is the same as, I don't know, let's see, let's subtract 5 row 1s from row 2, 0, -5. Let's subtract 2 row 1s from row 3, 0, -3, like that. What did I do? What did I do from this point? um, Interesting. Let's multiply row 2 and row 3 by 3. Uh, no, sorry, let's multiply row 3 by 5, so negative 15, 5, 5, and row 2 by 3, so negative 15, negative 3, 21. Okay, let's subtract row 3 from row 2. That will give us 0 minus 8 and 16. So this will simplify to 1, negative 2. We can subtract 5 row 2's from row 3. That will give us 0, 15. So this row will simplify to 1, negative 1. And then we can subtract it from row 1, 0, negative 1. So at this point, we are ready to rewrite our f of t using the ABC values that we had. And depending on how I cut this, you might have seen me just write a negative 1 here. It's actually 1. It was an obvious mistake. And I fixed it. Okay, so we have A, which is 1 over alpha minus 1. That's in a form that we really like. We can take the inverse Laplace transform of that, no problem. And then we have plus B alpha, which is negative alpha plus C minus 2, all divided by alpha squared plus 2 alpha plus 5, but I'm going to rewrite that as alpha plus 1 squared plus 2 squared. You'll see why in a sec, and that second is right about now. We are going to be using these two formulas over here, and we need to put this into a form that is usable for this. Since our value for A, in this case, is negative 1, we would like to see an S plus 1 on the top up here, so an alpha plus 1 in our case. Let's factor out a negative 1 from all this and see how we can split this thing up. So we want an alpha plus 1, so alpha plus 1 over alpha plus 1 squared plus 2 squared is a form that we like. And then we are left with a 1 over alpha squared plus 1, again, not squared, squared plus 2 squared. And I just had a little bit of a mental breakdown because this has taken a lot of takes that you haven't seen. This is a particularly crappy problem because I realized that we don't want a 1 on top here. We want our value of b on top, which is 2. But all we need to do that is multiply this by 2 and then multiply the whole thing by 1/2. So we are ready. We can take the inverse Laplace transform of f of t. This is not f of t. This is f of alpha. Let's take the inverse Laplace transform of f of alpha, and our first term will just be e to the t, 1 over alpha minus a, 1 over alpha minus a. That a value will go up into the exponent, so we get e to the 1t. Then secondly, we have our minus sign that was sitting out here all lonely times the quantity. Let's see what kind of Frankenstein we've made here. We have 1/2. Oh no, I'm going right to left. I want to go left to right. We have this guy right here, where our a value is negative 1. So e to the negative t cosine bt, where b is the value we have squared both here and here, cosine 2t. And then finally, we have plus 1/2 e to the negative t, and then this will be sine bt yet again, so sine 2t. Okay. And thank Thank God, B matches perfectly with what we found if you distribute out everything, and 16, 16 is B. Oh, God, that was terrible. 17, we are finding the Laplace transform of this guy right here. This is actually a lot more tame than it looks. We know that if we have some function we're trying to take the Laplace transform of, and it's formed from an integral from 0 to t of some function of t where all the t's are replaced with t minus taus. Let's identify that. So f of t minus tau in this problem up here is our sine of pi t minus tau. That's a little ugly, but you get the point. And then multiply by some function g of tau. Well, our g of tau is just anything up here that's left over. So tau squared e to the negative tau. And the Laplace transform of this is just the Laplace transform of f of t, which we know to be called f of s, multiplied by the Laplace transform of g of t. So let's rewrite these. We have f of t as sine pi t, and g of t is t squared e to the negative t. And we have individual rules for both of these, and we can just multiply things together at the end. So t to the n e to the at is n factorial. So let's see, we're solving the Laplace transform of g of t right now. That's n factorial, so 2 factorial, 2 divided by s minus a, so s plus 1, but I'm using alpha, so alpha plus 1, to the n plus 1, so cubed. And then we are multiplying this by the Laplace transform of f of t, which is just the Laplace transform of sine pi t. The Laplace transform of sine at is a over alpha squared plus pi squared. So multiplying all this together, we get, nope, that's an s, we want a pi. We get e, 2 pi over all that. 17 is e. Ooh, it's really raining. Maybe you can hear that. 18, find all the values for k for which the solutions to this system spiral into the origin as t approaches infinity. So this is all to do with the signs and the real or imaginary parts of our eigenvalues. So for this specific case, spiraling into the origin, we need a negative real portion of our eigenvalues and then our conjugate imaginary pair to add the little spiral to it. So we're solving the determinant of a minus lambda I equals 0, so negative 2 minus lambda plus k is equal to 0, or lambda squared plus 2 lambda plus k is equal to 0, setting up our quadratic formula. That is negative b over 2a, so negative 1, which is good. We like to see that negative 1. That's our towards the origin part of spiraling towards the origin, plus or minus the square root of b squared, so 4 minus 4k all over 2. And this thing is imaginary whenever k is greater than 1. If k is greater than 1, we'll get a negative sign under that square root. So 18 should be b. And I think I can put these away finally. 19, let's find the solution to this initial value problem right here. So we're using the eigenvalue method. We're going to find our eigenvalues first. That is negative 4 minus lambda minus 4 minus lambda. Minus 4 is equal to 0, or lambda squared plus 8 lambda plus 16 minus 4 is plus 12 is equal to 0. This is lambda plus 6, lambda plus 2, so lambda is equal to negative 2 and -6. -2 and -6. Okay. From this, we can, for lambda equals -2, find a minus lambda I. That will be -2, -2, 2, 2. We can simplify this down to 1, -1, 0, 0, and find an eigenvector of 1, 1 from this, because this is saying x1 is equal to, if we move that -1 to the other side, x2. And so the x1 position in here is just 1. For lambda is equal to -6, we end up with 2, 2, 2, 2, simplifying down to 1, 1, 0, 0. So we get our -1, 1 eigenvector. Setting up x of t at this point, because we can, c1 v1 e to the lambda 1t plus c plus c2 v2 e to the lambda 2t. So we can set up a little augmented matrix here with 1, -1, 1, 1, 1, 0, using the initial condition that they give us. Subtract row 1 from row 2, you will get 0, 2, -1. Let's see, we'll divide that out, 1, -1/2, and add it to row 1, 0, 1/2. So C1 is 1/2, C2 is -1/2. Looking around for that solution, we see that that matches E if we factor our -1 into our e to the -6t. So 19 is E. 20, let's consider this differential system. We're trying to find the fundamental solutions of this system. And because we're seeing t multiplied by some eigenvector and e to some eigenvalue t, we know that we're going to have a multiple eigenvalue here, and that we'll need to find a generalized eigenvector to fix our defective system. So finding these, or this single eigenvector, we're solving 1 minus lambda times -7 minus lambda plus 16 is equal to 0. Lambda squared plus 6 lambda minus 7 plus 16 is plus 9 is equal to 0. This is lambda plus 3 squared is equal to 0. Lambda is equal to -3. 4 lambda is equal to -3. A minus lambda I will give us 4, -4, 4, -4, 4, -4, which simplifies down to 1, -1, 0, 0, and we will get an eigenvector of 1, 1 out of the deal. So at this point, let's start making our x of t. This is going to be c1 v1 e to the lambda 1t plus c2, and then we need our double bracket v1 times t plus our generalized eigenvector, which we haven't found yet, e to the lambda 1t. And I should have been clear up here, it's lambda equals -3 with a multiplicity of 2, just putting that little m squared in there to denote that. So finding this generalized eigenvector, we're going to take a minus lambda I, so 4, 4, -4, -4, and set it equal to our eigenvector, so 1, 1. And simplifying this down, we can divide everything by 4, 1, 1, 1, 1, 1/4, 1/4, and then use row 1 to set row 2 equal to 0. And once we get it into the form that we had it in when we solved for our first eigenvector, whatever is left here on the right is our generalized eigenvector. So we get 1/4, 0 in there. And so our fundamental solutions are just the things that are attached to C1 and C2. So we're looking for 1, 1 e to the -3t. That's looking good, and that's looking good. And then 1, 1t e to the -3t and 1/4 on the top over 0, e to the negative 3t. So C should be our answer for 20, which it is. Okay, we're done. And this is my last video for today, so I get to go, I don't know, not doing anything fun, that's for sure. Okay, see ya.